Our third speaker today is Vlada Kalinic, who's from OneSpin, which is now a Siemens business. He's a product specialist on SystemC, and he's going to talk about using formal verification for easing the SystemC C++ verification burden. As I say, he's a product specialist of SystemC at OneSpin. Was involved in evaluations with new customers as well as supporting current portfolio to improve the SystemC C++ verification flows. He holds a master's degree with honours in electrical and computer engineering, embedded systems and algorithms from the University of Novi Sad in Serbia. Prior to Mentor or Siemens now, Vlada worked with OneSpin for 5+ years and was involved in various successful evaluations with SystemC customers. So over to you, Vlada. Thank you very much.
Okay, thank you, Mike, for the nice introduction. So yeah, today I will talk about formal verification for the SystemC C++ designs in the DV world. Okay, so let's go quickly through the agenda. So I will talk about introduction to the OneSpin and then overview of HLS, so high-level synthesis usage, current challenges in the EDA industry, and what type of opportunities there. Also, I will talk about OneSpin solution with SystemC DV tool, inspect and verify. And at the end, just a Q&A with a summary. Okay, so just quickly about OneSpin. So OneSpin is a company that is based mostly in Munich, Europe. So our headquarters is in Munich, and OneSpin is based on formal engines that have different solutions to functionally verify correctness of your design, also to verify safety, security, and trust of your ASIC, FPGA, and different designs. So as OneSpin has different solutions, today I will talk about functional correctness for designs. Just once again, so OneSpin is a formal based tool with formal platform that has different technologies that can handle new designs in industry. So next to the SystemC, we can support VHDL, Verilog, System Verilog, and other types of designs. Okay, so let's start with SystemC. So in SystemC, sorry, okay, in SystemC today, SystemC is mostly used for HLS modeling, and because with SystemC, as it is one level above of abstracting of your design, you can resolve some problems much easier with the writing some kind of mathematical operations of design types and similar algorithms with SystemC much easier than compared with regular RTL like VHDL or Verilog. But with SystemC, that with the modeling, it creates some new problems and also opportunities. So there are various types of algorithm implementation issues in SystemC, as well as some SystemC language related code problems, and also functional consistency checking of SystemC and produced RTL. So some common used HLS design flow looks like this one. So starting with the floating point algorithmic design towards fixed point implementation in C++, then getting SystemC HLS model that can HLS tool can read in and can execute with synthesizing, and then getting the synthesized RTL from the HLS tool. So that's the common HLS design flow that is used in the industry today. Just quickly about the standard. C++ standard is not built for hardware descriptions, and that's the reason why SystemC language is introduced. So it is covered by IEEE standard, but the standard SystemC itself has some unspecified and also undefined situations that are not fully covered by the standard. So this is also the reason why verification on the SystemC level must be covered just to avoid any functional mismatches between the SystemC and generated RTL. Okay, so currently in the EDA industry, when the companies are using the SystemC as a language description for their design, so the current HLS flow looks like by generating the algorithm modeling in C++, then getting the HLS code in SystemC or C++, that is synthesizable to be synthesizable in hardware, then importing that HLS code in high-level synthesis tools, and then this high-level synthesis tool will produce the generated RTL. And challenges for this flow is that there is some limited useful feedback from the HLS tool, and also some coding mistakes can cause simulation mismatches that are very difficult to debug. Why? Because generated RTL is very unreadable because it is generated by the synthesis tool, and it is very difficult to find the issue on the RTL code and then to port back to find the root cause, what is the issue on the original SystemC code. And also, if the SystemC code has some issues, mostly or often the high-level synthesis tool will also produce the same problem for the generated RTL, so we can call it a garbage in, garbage out approach. So these are all the reasons why the current commonly used HLS flow should be improved. And so OneSpin has solution to verify the HLS code before sending that code to the high-level synthesis. And that's why the OneSpin tool should be placed in the middle of the process and to discover the problems much easier before running the HLS synthesis. Some of the solutions and benefits is that the runtime of the verification is much faster because the loop is much shorter. You don't need to wait for high-level synthesis to be finished and then to check the correctness of the generated RTL. So you can start much earlier the process to verify the HLS code itself and then to debug if there are some issues. And it is also much better to verify the SystemC because you can discover the problems much easier, and because it's more readable to verify that on original SystemC code. So OneSpin, as I said before, is a pure formal. So they are auto checks, or we're also calling that superlint. as automated apps, and also we are additionally supporting manually written assertions like SVA or PSL or similar. Okay, so just an overview what type of apps our OneSpin SystemC solution has. So firstly, we have a standard app portfolio for automated formal analysis. So like calling a DVInspect. So there we have structure analysis, linting, superlinting, initialization and reset checks, overflow and array out of bounds checks, activation and reachability like unreachable or dead code checks, arithmetic precision and race conditions and so on. So on this green part, these are all checks that are automatically generated. So it's almost a push button approach. Then as an add-on, so we have additional app that we're calling DVClub that has internally several applications like design exploration and XProbe, protocol verification IP for the AMBA protocols like X84, X83, APB, and so on. And also we have a scoreboard for following the data protocols there. By the end, as I said, we have a DVClub with formal ABV, so user can additionally write manual written assertions like system value assertions, also C-assert we support, and also cover points, observation coverage, and also additionally your user can write any type of constraints assumes. So these are what kind of our portfolio for SystemC solutions is supported internally. So let's start additionally to go deeper in the first solution that I mentioned. So it's DVInspect or auto checks that are automatically generated once the SystemC design is ported into the tool. So just to give you an overview, what type of different auto checks we have. So as I said, we have initialization, array out of bounds, function without return, division by zero, write, read-write traces, truncation or overflow, integer or redundant bit checks. Also we support fixed overflow, shift negative, signal domain. Also we can check the FSM table from the SystemC design, stick or toggle checks, dead code or unreachable code, and also X propagation. So what are the key values that OneSpin tool needs? So with OneSpin SystemC solution, you can eliminate design bugs before running HL synthesis. And as I said, it is a pure push button flow. So there is no need to write any stimulus, neither test bench. So you can just read your SystemC design, compile, and then all these checks will be automatically generated, and then you can tell the tool to start the checking of that. So also verification process can be started much earlier in the process. So you don't need to wait for the HLS to finish. So you can start much earlier. And because of this benefit to not write any stimulus, so you can reduce simulation effort in your SystemC and also RTL verification process. And also one of the key benefit of our tool is that you can optimize your HLS code and to give this optimized code to the HLS input to get for the HLS the code that is already optimized in order to reduce the effort, but also the runtime for the HLS to be finished. Okay. I will not talk too much detail about all these checks that we have, but just to give an overview what is supported in the OneSpin, and also with explanation of each of these categories that represent each category by itself. So there are definitely various types of categories that are covering the most pressuring issues that can be found in various customers' design that exists currently in the industry. And all these checks we implemented by the time. Also, some of these checks we implemented by customer requests that are currently very valuable for them during their verification processes. Okay, so currently our standard GUI view looks like this on the screen. So you can view the instance hierarchies and also the port list of input, outputs, internal states, and so on. Also, you can see the active code, and also you can go through the code with the driver and load tracing to follow the hierarchy propagation. Let's start now with some problems in the SystemC designs and SystemC flows. So definitely how SystemC is handling the initialization part, because that can predict some unknown issues. So you know that by the standard, by the synthesizable standard, module constructors' initializations are ignored by the standard. And the reason is because recipe behavior should be under user control. So that means if you have some register that is not initialized, these uninitialized values can propagate through the design and can propagate through the logic by the output, and also your output can have some X values by the end. So this is what can be wrong, and SystemC has no concept of X state because that's undefined by the standard, and as that is not defined, so but OneSpin has support for the X values checking. So definitely that is worthwhile to check what is uninitialized and what can cause potential X on the output side. Okay, this is just an overview how our GUI looks like when some outputs or states are not initialized. So we are reporting that as fail, marking that with red, that you can debug that, just indicate what is potential X. Okay, let's continue with undefined values. So as I said, uninitialized registers can be potential sources of X. So X can propagate to the output, but also there are other sources of X, so like undefined operations, like array out of bounds, but also multiple drivers like write traces or read-write traces simultaneously. So all these types can cause X by the end, and as that can be wrong. So what are the solutions? So SystemC simulators has no notion of undefined values or RTL semantics, but OneSpin as a formal engine can exhaustively analyze all conditions under which an X can be propagated on the output. Okay, so but also formal is excellent for identifying uninitialized states and examining how these X can be propagated through the design. Okay, so I will talk. So continue undefined operations. So array out of bounds can also cause undefined values like x, and these are very hard to be spotted on the simulator or random simulation type of verification. But formal and the OneSpin can easily detect if we have array and out of bounds that are happening, so we can easily identify that violation exists in your design with arrays. Just some examples. Also, if the tool detects violation, so we will mark that fail. And when you double click on that check, so we will open the fail code with counterexample with active code. Then you can debug that and propagate follow the driver tracing of that. Okay, as I said, SystemC Races. So these races can also be the potential sources of X. So like write or read write races. So the SystemC simulation is purely sequential. So standard forces simulator to execute threads sequentially, but the hardware is concurrent. So RTL processes work in parallel. And our tools support parallel process execution. So that's why we can detect races that are happening at the same time on the different processes. Okay, as I mentioned, so OneSpin support fixing point precision app. So we can check the overflow or truncation. So if overflow can happen in your design, so OneSpin will report that overflow can be executed, and also user can debug why that is happening. Also, this is to check that it's fully automation, so no need for stimulus. And also, we can prove the absence of overflows in your design. Otherwise, we will create counterexample that you can debug. On the other side, also we can check for redundant bits. So that is checking that upper mode bits are redundant. This is also automated, no need for stimulus. And by this check, you can optimize your design to shrink the bit width of your internal signals. So just an overview of what type of redundancy and overflow we support in SystemC types, so like SCU int, SC fixed integer, and sign W integer types. Let's continue. So as I mentioned, also we are supporting unreachable checks like dead code checks. So by the formal, you can exhaustively analyze as automatic solutions what type or which parts of your designs are always unreachable.
Vlada, just a reminder, we've got 1 minute left.
Okay, yeah, I'm very close to the end. Okay. Let's continue with toggling. So stack or toggle checks. So we can check that all bits are toggling from 1 to 0 and from 0 to 1. Yes, some other capabilities. So we are also supporting manual written assertions. So user can write SVA assertions and can check some manual functionality of your SystemC code as well. Just to speed up, yeah, that's also some sentences about SVA assertions that we additionally support. Okay. And also we have a very close partnership with the HLS tools in the industry. So we support many others libraries from well-known HLS tools that are available on the market. Yeah, that's pretty much everything that I wanted to tell you. And so if you have any questions, please let me know if we have some time.
So, Axel, thank you very much for the presentation. Unfortunately, we have no time for questions. There are quite a few Again, we'll do them by email because we've run out of time. But thank you for the talk. I verified, I worked on verification of a complex SystemC design a few years ago, and it is quite complex to do, so having tools like this would have helped a lot of the time. So thank you very much for that. We'll put those slides online as well in case there's some material there that we didn't get to cover, and we will send you the questions by email. So thank you very much. Thank you.